Hello students. So I'll be teaching you the subject advanced instrumentation in this semester. So the syllabus of advanced instrumentation covers radiation sensors, that is we'll be learning about all the optical sensors, then we'll study about smart sensors, then we have piezoelectric transducers, then you're going to study about the elements of electronic, pneumatic and hydraulic controllers, measurement of pH, conductivity, viscosity, etc. Then digital transducers and pipelining and instrumentation diagram, and study of hazardous condition in industry. So these are the topics that you will be covering under this subject. So we'll start with the radiation sensors, and for actually going into the deep of this topic, you need to know some basic terms, or you can say the prerequisites for the better understanding of this topic. So let me discuss what is electromagnetic spectrum. Basically, as you can see, this is the electromagnetic spectrum. The wavelength is given and we have the frequency, and as you can see, this whole is the electromagnetic spectrum, and the optical spectrum, that is ultraviolet, that is consisting of ultraviolet, visible and infrared. This optical spectrum is covering a very small portion of this electromagnetic spectrum, and in that optical spectrum also this visible portion, or you can say the visible spectrum, is covering very small part of this whole electromagnetic spectrum. So here it is given the wavelength of all the regions in the electromagnetic spectrum, as well as frequency is also given here. As I've told you that the optical spectrum in the electromagnetic spectrum consists of very small part, and it is divided into three regions like ultraviolet, visible and infrared. So it is covering a wavelength range from 10 nanometer to 10 to the power 6 nanometer, means this wavelength. The ultraviolet, visible and infrared up to this wavelength. This is the optical spectrum wavelength. Now in this optical spectrum we have this ultraviolet region. This ultraviolet region is further divided into extreme ultraviolet, far ultraviolet and near ultraviolet. The wavelength ranges of these regions are also provided here. I've shown here. Then we have this visible region of this optical spectrum, which is having the range from 370 nanometer to 770 nanometer, and the last region of this optical spectrum is infrared region, which is further divided into a number of regions like near infrared, middle infrared, far infrared and far infrared, and the wavelength ranges for these regions are provided here. So this is the electromagnetic spectrum, this is the optical spectrum, and this is the visible spectrum, visible region of this optical spectrum. Now we also know that these are the prerequisites that I'm going to tell you, because you might be needing these terms for the understanding of future topics. So we also know that frequency of light is related to the wavelength of light by the relation F is equal to C by lambda, where C is the speed of light, lambda is the wavelength of light, and F is the frequency of light. So here you can find, if you know the wavelength of the electromagnetic spectrum or the wavelength of different regions in the electromagnetic spectrum, so by this relation you can easily find the frequency also. Now moving on to the next topic, the next term that we need to know is optical detectors. So what are optical detectors? You can say optical detectors, or you can say optical transducers. So basically this is a light sensor, you can say this is a transducer. Optical detector is a transducer which converts the incoming light energy into the electrical energy. So this electromagnetic spectrum, this is the light. So it converts the incoming light energy into the electrical energy. The purpose of optical detector is this. Now, in instrumentation systems, measurements are not confined to visible radiation of light only, but are concerned with a wider spectrum of radiation, including infrared and ultraviolet. Now, moving on to the next term is threshold wavelength. So, what is threshold wavelength? Let me discuss. First, we know that the quantum theory of light, it states that energy of each photon, first of all, the quantum theory of light states that the light exists in the form of photons, and the energy of each photon is given by E is equal to h nu, where h is the Planck's constant and nu is the frequency of light. So in somewhere I've used f, in some places I've used nu. Both means the same thing, that is the frequency of light. Now the Planck's constant, what is the value of Planck's constant? We know it is 6.623 into 10 to the power minus 34 joules per second. It is 6.623 into 10 to the power minus 34 joules per second. This is the value of Planck's constant. So, as I was telling you, as per the quantum theory of light, light exists in the form of photons, and each photon is having the energy E is equal to h nu, where h is the Planck's constant and nu is the frequency of light. Now, this relation can also be written in this form also, as I've already told you in my previous slide, that frequency of light is equal to c by lambda. So I'll replace nu by c by lambda. So E is equal to h into c by lambda, or you can say from here h is constant, Planck's constant is obviously a constant, c speed of light, it is also constant, that is 3 into 10 to the power 8 meter per second, and then we are left with this lambda. So we can say that E is inversely proportional to lambda, or you can say the energy of photon is inversely proportional to the lambda, or you can say the wavelength of light. So as we know that light exists in the form of photons, the energy of photons is indirectly proportional to the wavelength of that light. Now, since I have told you that E is inversely proportional to lambda, or you can say that energy of photon is related to the wavelength of light, so we also know that for different colors of light, what does it mean? Light is having different colors means the wavelength of light is different. So for different colors of light, the light is having different wavelengths, and for different wavelengths, from this relation we can say that the energy of photon of that light is also different. So again I'm repeating, what is happening if the light is having different colors, for that different colors the wavelength of radiation is also different, and for those radiations the energy of photon is also different. Now when these photons strike a surface such as a cathode surface, the whole energy of that photon goes to the electron. It either gets converted into the kinetic energy of the electron. Now when the energy absorbed by the electron is more than the energy required by an electron to break the bond and come out as a free electron, then the electron will come out as a free electron. So what I'm trying to tell you is that depending on the different colors of radiation, the wavelength of light is also different. Depending on the different wavelength of radiation, the energy of those radiations are energy of those photons are also different. Now depending on the different photon energy for respective wavelengths, the output of optical transducers will also be different. Means whenever a photon suppose we have two different colors of light. We have two different colors of light, and for those two different colors of light, the wavelength of those two light will be different. The wavelength of those two photons of those lights will be different. Now there is a surface, there is a cathode surface for which one particular photon may be able to excite the electron in such a way that the electron will come out as a free electron, whereas the other photon of the other light may not be able to excite the electron up to that extent, so that the electron may not come out of as the free electron. So in this way you can say the output of optical transducers, the output of optical transducers will be different, because what is the purpose of optical transducer? The purpose of optical transducer is to convert the light into the electrical energy, or you can say into the number of electrons coming out of the cathode surface. What is electrical energy? Is the number of electrons, or you can say the charge. So depending upon the wavelength of the light incident on a surface, the output of optical transducers will get affected accordingly. Now there is a threshold wavelength. There is a threshold wavelength for or you can say there is a particular wavelength at which the energy imparted to the electron is equal to the energy required by the electron to be liberated or to be free. So you can say this E dash is equal to EW. What is this E dash is equal to EW? It is the kinetic energy of emitted electrons. So when at a particular wavelength, when the energy imparted, that is this energy imparted to the electron, that is this photon energy imparted to the electron means the photon energy which is going to get imparted to the electron. When this energy will get equal to the kinetic energy or the energy required by the electron to be liberated, will get the threshold wavelength there only. That is, by equating equation 1 and equation 2, will get the value of threshold wavelength, which is equal to hc by EW. Now since h is Planck's constant, c is the speed of light in vacuum, E is the charge of each electron, which is equal to 1.6 into 10 to the power minus 19 coulomb, and by placing all the constants, or by replacing the constants with their values, that is replacing h with its value, that is 6.634 into 10 to the power minus 34, then replacing c with its value, that is 3 into 10 to the power 8 meter per second, and replacing E with its value, that is 1.6 into 10 to the power minus 19 coulomb. Putting all these values in the equation and calculating, will get the relation like this: lambda, that is the particular wavelength, or you can say the threshold wavelength, is equal to 1.24 into 10 to the power minus 6 divided by EW. So what is this EW? EW is this EW is the work function of that material on which the photon is going to strike to liberate the electrons. So lambda is the threshold wavelength which needs to be struck. So it is the threshold wavelength which needs to be strike on a surface, or on a cathode surface, or on a material from where the electron is going to come out. So it is the threshold wavelength which needs to be struck so as to liberate the electron from the material. Now this is the wavelength. We know frequency nu is equal to c divided by lambda. So if we can easily calculate the frequency from this wavelength, that is we can also calculate the threshold frequency. Now if the frequency of any spectrum of light, suppose for a material we have found the threshold frequency. Now if the frequency of any spectrum of light beyond the threshold length, then there will be no response from an optical transducer, means no electron will come out from that surface if the frequency striking that material is beyond that threshold frequency. So I'm ending this class here. In my next lecture we'll be solving a few numericals based on this threshold wavelength formulae. Thank you. I'm ending this class here.